Hello everybody and welcome to today's video where we're going to be making a goal-based vector field for pathfinding. This is something that's also known as a flow field. And today we're going to be implementing it in the Unity game engine. Now this video is a part of a series of videos that I'm doing on the flow field. And if you want an example of what a flow field looks like, you can see it playing right behind me. And if you do want some more information on what exactly the flow field is and how the whole algorithm that we're going to be implementing today actually works under the hood, definitely go check out the first video in the series that I made. I'll link it in the card as well as in the description below. Again, that's going to serve as an introduction to this whole series to get yourself familiarized with what flow fields are before we can go ahead and implement them like we are doing today. So today, like I said, I'm going to be implementing it in the Unity game engine. We're just going to be using some typical Unity mono behaviors, but I wanted to do this as a little bit of an experiment because I also want to implement this with Unity's new data-oriented technology stack using their entity component system. And then kind of once we have these two different flow fields, we can compare the performance between the two. And I think it's going to make for some really interesting videos. So anyways, to make sure that you don't miss out on any of those fantastic videos, make sure you are subscribed to the channel. Of course, if you have any questions on any of the stuff that I'm going over today, feel free to drop that all down in the comments section below. And if you did find this video helpful, I'd really appreciate it if you hit that like button as well. So today's video is going to be broken up into a total of 5 sections, and so those sections should all be displayed down in the timeline below. So essentially what we're going to be doing today is we're first going to break up our world into a grid. After that, we're going to be able to implement our cost field. Then we'll do our integration field, and once we have that, we can actually make our flow field. Then once we have our flow field, I'm going to show you how we can actually have some objects in our game move around our game world using the flow field. Now, there are a few additional things that I'm going to be doing in today's video that fall slightly out of the scope of all of this. So I'm going to be just kind of explaining what that is and not necessarily going into any detail. But if you do have any questions on that stuff, you can ask it down in the comment section below as well. And I should mention that all the project files and scripts and everything will be available using some links down in the description below. All right, so here we are in Unity. I just have a mostly empty project and I've just imported a couple assets. But basically we're going to be creating a 3D world, although we're going to be working in 2D space. So you'll see that I have this camera set to orthographic projection here. So we can just basically leave this in top-down 2D mode for now. So basically this is kind of our game world, is just this big patch of grass here. And so the first thing that we need to do is actually break it up into a grid. And so our grid is basically going to be made up of a number of cells. So we can go ahead into our scripts folder here and we'll go ahead and create a new C# script and we can just call this cell. So just go ahead and open this up in your IDE of choice and go ahead and clear out everything in here. Now the first thing is we're just going to need to, of course, import the Unity engine library. So here we'll just create our public class called cell, and you'll see that it's just a plain old C# class. It's not inheriting from mono behavior or anything like that. So of course we want to know where our cell lives in the world. So we're just going to create two public variables. One is a vector3 for world position, and the other is a vector2 for int for the grid index. And so that's going to represent essentially the XY coordinates of where this cell lives on the grid. So now we'll just go ahead and create a constructor for this class, which is going to take in a vector3 for the world position and a vector2 int for the grid index. And then of course we can just set those values in the instructor. And that's all we need to do for now for our cell class. So we can just go ahead and save this and come back to Unity. So now that we have our single individual cell, the next thing that we want to do is actually create a grid of all these cells. So here we'll just go ahead and create a new C# script. And this is going to be our flow field class. So again, we can clear out most of the stuff. We're just going to do another plain old C# class for this flow field. So first we're going to start off with a couple of public variables. The first is going to be a 2-dimensional array of cells, which we can just call grid. And this is going to allow us to access any of the cells on our grid. As you can see, we have set it to public get and private set. Next up, we have a vector2 int for the grid size. Again, this is a public get and a private set. And then finally, we have a public float for cell radius. Again, public get, private set. And we do just need one private float variable for cell diameter. There are a couple cases where it's going to be nice for us to have a cell radius and a cell diameter component. So now we'll create the constructor of our class. Of course, it's going to be a public flow field, and it's going to take in a float value for the cell radius and a vector2 int for the grid size. And then here we just set the cell radius, cell diameter, and grid size. So of course, one of the most important functions we're going to need is a create grid function, so it can actually initialize all the values on the grid. So here we'll just initialize our grid array to be the same size as we defined in the grid size value. So now we'll just do a nested for loop starting at 0, going all the way up to grid size.x and grid size.y. So at each of those locations, we're going to go ahead and define the world position of our next cell. So we'll just create a new vector 3, and then for the x value, we'll just do cell diameter multiplied by the current x value. And we'll add in cell radius for just a small little offset, set the value of y to 0, and then for the z value, we'll do cell diameter multiplied by y, and then add in the cell radius again just for that little offset. So then at grid position xy, we'll create a new cell passing in values for the world position as well as the current grid index, which of course is xy. So we're all finished up with the flow field for now. Now we'll come back to Unity and we'll create another script here. So I'm going to create a grid controller class, and this is what we're going to be using in Unity to set the values for our grid as well as call functions like actually creating the grid. So just go ahead and clear out these start and update functions. So we're going to start off with a couple public variables. So the first one is going to be a public vector2 int for the grid size. So this is going to be where we actually are modifying the grid size within the Unity editor. Next we'll do a public float for the cell radius, and so we'll set that equal to 0.5f so that each cell is going to be 1 unit wide, and if we ever wanted to change it in the editor, that's right where we can do this from. And then finally we'll just have a public flow field for the current flow field. Now we'll just create a private function to initialize our flow field, and within there we'll just go ahead and set the current flow field equal to a new flow field, passing in our cell radius and grid size, which we've set in the Unity editor, and then we can just call curFlowField.createGrid. So now to actually call the initialized flow field, right now we're just going to go ahead and go into our update function, and for now we'll just set it to when we click the mouse button, we'll just go ahead and initialize the flow field. So when we're back in Unity, we're just going to go ahead and create an empty game object, and so this is going to be our grid controller. So just bring the grid controller component onto it, and with how I have it set, a grid size of 40 by 22 and a cell radius of 0.5 should basically make a grid across this whole field here. So of course we can hit play, and then when we click, it will actually generate the grid of all the cells. However, we can't see it, so I've created this little debug class, and this is one of those things that I'm not going to go into super detail on. So here I just have this grid debug class, and within the onDrawGizmos function, basically it just calls this draw grid, so we can get a visual representation of the grid within our game world. So now with this grid debug component that I made, basically we can kind of get an idea of how big this grid will be when it's in our game world. And then if we actually enter play mode and click, you'll see that the grid changes green to basically confirm that we have actually initialized the grid, and this is the size of all the cells. So now that we have our game world broken up into a grid, the next thing that we're going to do is implement the cost field. Now this is the part that's kind of up to you as a developer. Basically the way that I'm going to be doing it today is we're going to be having some kind of patches of rough terrain, and then we're going to be doing a check to see if any of these grid boxes fall on top of that rough terrain, in which case we'll go ahead and increase the cost. And then also we're going to have some impassable walls that our flow field is basically going to navigate around. Now again, this is really up to you as a developer about how you want to implement your cost field, so just kind of play around with some of the values and find what fits right for your game. So one thing that we're going to do is just go over to the project settings, and we're going to create a couple new layers. So we're going to have a layer 8 is going to be impassable, and then layer 9 is our rough terrain layer. So what I'm going to go ahead and do right now is create some of this in our game world. So for the rough terrain, it's basically just going to be some planes that are on the rough terrain layer. And then for the impassable walls, they're going to be some cubes which are on the impassable layer. All right, so I've just created a super basic little scene. Of course, we just have some rough terrain in here as well as some impassable walls, just to get an idea of kind of how this flow field flows around all the impassable walls and tries to avoid some of this rough terrain in some cases. So we'll come back to the cell class and go ahead and add in a public byte for cost. So a byte is just an integer value that can be anywhere from 0 to 255. And so we're going to use this as the cost of our individual grid cell. Now in our constructor, just by default, we can go ahead and set this cost equal to 1 because that's essentially the default value of cost on a flat ground. So now we need some way to increase the cost of a given cell. So we're just going to go ahead and make this increase cost function, which takes in an integer for the amount to increase by. So first we just got to do some checking just to see if the cost is already equal to byte.maxValue, which is 255. If that's the case, we can just return out of the function because we can't increase the cost any higher. Also, if the amount plus the cost is greater than 255, we're just going to go ahead and clamp the value of the cost to 255. Again, it being a value of 255 makes this an impassable cell. Otherwise, we can just go ahead and add in the amount to the current cost value. All right, so now in the flow field class, we're just going to go ahead and create a new function called create cost field. So basically what I'm doing here is just looping through every cell in our grid and doing a physics.overlap box at the world position of the current cell. And that overlap box is basically just on this one terrain mask, which just looks at the impassable and rough terrain layers. And if it hits anything on any of those layers, if it is impassable terrain, we're just going to go ahead and do curCell.increaseCost by 255, which will bring it all the way to the max value of 255. Otherwise, if it did collide with some rough terrain, we're just going to go ahead and increase that cost by 3. And also have this has increased cost flag right here. And the reason I do that is because if there's like a cell that collides with two pieces of this rough terrain, I don't want to increase the cost twice. I just want to increase it one time. So again, this is my implementation of how to create a cost field. And this is something, again, that's up to you as a developer to figure out how you actually want to generate your cost field. And then in our grid controller, right after we initialize the flow field, we can just do a curFlowField.createCostField. And then in my grid debug class, I'm just going through every cell and doing a handles.label, basically just debugging the current cell cost. And so if we go over to Unity and enter play mode and just click anywhere on the field, you'll see that it creates this full cost field here. Now you'll notice that basically everything on this grass is a 1, everything that's touching this rough terrain is a 4, and then everything that's touching these impassable walls is a 255. That is a beautiful looking cost field. All right, so next up is the integration field. And with the integration field, we're basically going to be adding up all these cost values so we can create our full integration field. All right, so for the integration field, we're going to need some notion of direction so we can kind of look at some of the neighboring cells. This is the grid direction class that I've created, and I'll just give it a quick scroll here. But you can see that basically what we're doing is we have this vector2 integer for a direction, and then that direction corresponds with one of the directions, you know, like north, south, east, west, as well as some of the intercardinal directions like northeast, southeast, southwest, and northwest. And so I've also included these static lists for all directions, cardinal and intercardinal directions, and cardinal directions. And this is going to be shorthand for us to get some of the neighboring grid cells. Again, you can download this using the link in the description below. All right, so in the cell class, we're just going to go ahead and create a public ushort best cost. So ushort is an unsigned short integer, and in our constructor we'll just go ahead and set the best cost equal to ushort.maxValue, and the max value is 65,535. So by default we just want this best cost to be set to a really high number, so then when we compare it with some of the other numbers around it, then they're going to be lower, and then that's how we can kind of determine the best direction for our flow field. All right, so in the flow field class, we're just going to go ahead and create a public cell for the destination cell, because now that we're doing the integration field, we actually need to know where our final destination is going to be. And then at the bottom, we'll just go ahead and create a new public function called create integration field, which takes in a cell type called destination cell. So of course, we'll just go ahead and set the destination cell in our class to the destination cell that we're passing into the function. So now we'll just set the cost and the best cost of the destination cell to 0. So here we'll just go ahead and initialize a new queue of cells called cells to check. And then we're just going to go ahead and do an end queue, which basically just adds the destination cell to the end of the queue. And because the queue is brand new, it's going to be the only element in the queue. And so we're going to be doing a while loop. So we're going to be doing all these steps as long as we have cells within our queue. So we use the dequeue function to grab the cell at the front of the list and cache that as curCell. So next we're going to get a list of the neighboring cells in the top, down, left, and right directions. And so I do that through a helper function called getNeighborCells. So basically here we just pass in the grid index of the current cell, as well as the directions that we want to look for neighboring cells. In this case, we're just going to do the cardinal directions, which are north, south, east, and west. So then here's the helper function for the neighboring cells. So then basically we just take this list of directions and we loop through that, and then we use another helper function called getCell@relative_position, and here again we pass in the node index and the direction, and then the getCell@relative_position basically just finds the neighboring cell in the position that we're looking. So not super important how the flow field works, but basically this is just a way to get a list of the neighboring cells. So now we're just going to go ahead and loop through that list of neighboring cells. And so first we'll look to see if the cost of the neighboring cell is equal to the max value, in which case it is an impassable cell, so we can just go ahead and skip that. So now we're going to check to see if the cost of the current neighbor that we're looking at plus the best cost of the current cell that we're looking at is less than the best cost of the current neighbor. So what exactly does that mean? So if we're starting at the destination and the best cost of the destination is 0, and then we're looking at up, down, left, and right, all those neighboring cells are going to have a cost of 1. And if you'll remember, all the regular cells by default are set to a best cost value of 6,535. So now, of course, if we add the current neighbor's cost of 1 with the best cost of the current cell of 0, then of course that's going to be less than 65,535. So we'll go ahead and set that value to be the best cost of that current neighboring cell. And then after that, we're just going to go ahead and add that neighboring cell into the cells to check queue. So now if you think about it, when we go to that neighboring cell, its best cost is going to be 1, and then we look at its neighboring cells, which are all by default going to have a cost of 1. We can add the best cost of the current cell, which is 1, with the cost of the neighboring cell, which is also 1, so we get a value of 2. Again, that's going to be less than 65,000. So then there, we'll set the new best cost to be a value of 2, and then we're going to go ahead and add that to the open list. And so this just kind of like simple arithmetic and comparisons is basically how we can find the most efficient path from any possible spot on our grid all the way to the destination cell. And then one last thing, I do need to add in another helper function. So this is getCell_from_world_position. And so what this is going to do for us is when we click somewhere on the grid, then we can actually get the cell that we're clicking on, and then we can set that as our destination cell. All right, so now we'll just go ahead and come to our grid controller class. We'll go ahead and get a reference to the mouse position just using input.mousePosition x and y. Now we'll convert that from screen space to world space using the camera.main's screen to world point function. Next, we're going to get a reference to the destination cell, and we're going to again find that by going to the current flow field and doing a getCell_from_world_position, which is that helper function that I just implemented, passing in the world position of the mouse. And then after that, we can just do a cur_flowfield.createIntegrationField, passing in our destination cell. And then one more time, here is the grid debug class, where we're going to be debugging the best cost using the handles.label. So that's how we can see the integration field. So now you'll see when we click on the grid, you'll see right where I click, we now have a 0 for our destination cell. And then if I go over to my grid debug and I change the current display type to the integration field, now you see the integration field is displayed. So now at the destination, we still have a 0, and then going out from there, we now increase by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And then you'll notice when we get over to this rough terrain, these values start increasing by 4. So we have 11, 12, 13, 17, 21, 25, 29, 33, 37, 38. And then so after that, we'll see that we have a number 35, which is lower. So that's probably because it found a shorter path back to the destination, as opposed to going over this rough terrain. And then you can kind of also see on the impassable walls, basically we have the values of 65,535 set for the best cost of these impassable walls. So that is the integration field, and now comes the part that you guys all came here for, which is making the flow field. So in the cell class, we'll just go ahead and add a new public grid direction called best direction, and then in our constructor we can set the best direction equal to grid direction.none. So now in the flow field class, we can just sneak in a new function called create flow field, and we're just going to go ahead and iterate through every cell in our grid. So again, we're just going to go ahead and get a list of all the neighboring cells. This time around, we're going to use grid direction.allDirections. And so that's how we can not only get north, south, east, and west, but all the directions in between. So, like northeast, northwest, and the all directions also includes direction.none. So we actually are going to be comparing it with itself. So to keep track of the current best cost, we're just going to take an integer best cost. We'll set that equal to curcell.bestCost. So now we'll actually loop through all the neighboring cells. And so if the best cost of the neighboring cell is less than the best cost that we've already found, now we're going to set the best cost equal to the best cost of that neighboring cell. Then after that, we'll assign the best direction of the current cell using a helper function on the grid direction class, which I call get direction from v to I. So this is a helper function where we pass in a vector2 int, and then we get a direction from that. So here we can pass in the cur neighbor.grid index minus the cur cell.grid index. And this is basically going to return a vector that starts at the current cell and points to the current neighbor. And so that's how we can have a reference to the best direction. So anyways, basically we're just going through every cell on the grid and comparing it with its neighboring cells and finding which cell has the lowest cost. And whichever cell is the lowest cost, we're basically going to point to that. Now the only time that a cell will have a lower cost than all of its neighboring cells is when that cell is the destination cell. And one thing to note is that in my implementation, the impassable cells also will have a direction. And the reason for that is in my implementation, you'll see that I have the walls and they're not perfectly aligned with the grid. So even though the cell is impassable, it's possible for some of the units to actually navigate onto that impassable spot on the grid. And basically I just wanted a way to kind of push the object back into a valid location on the grid. Of course, in the grid controller, we're just going to need to do a cur flow field dot create flow field. And for the grid debug for this one, it gets a little bit more complicated, but basically I just have some sprites that are going to be displayed depending on whichever direction is the best cost. So when we come back to Unity and enter play mode, you'll see that now when we click on the grid, so you'll see that we have this destination cell here, and then we've marked off all these cells which are impassable. And then on this rough terrain, you can kind of see that things are trying to avoid some of the thicker areas of rough terrain. And so you'll see that we can click around on all different spots on our grid and a new flow field is generated each and every time. So now that we have our flow field finally being displayed in our world, the last step that we need to do is actually create some objects that will spawn in our world and can follow this flow field all the way to its destination. So I've just went ahead and created this pink little sphere called unit, and I've set it to a scale of 0.25 in all directions. Only other special thing that I've done is went ahead and add a rigid body component to it. So we can just go ahead and drag this into our prefabs folder here and just delete this one out of the game world. So now in our hierarchy, I'm just going to go ahead and create a new empty object, and this is going to be our unit controller. And so this is what we're going to use to actually control the units. So we can just go ahead and create a new C# script. Of course, this is going to be the unit controller, and we can just drop that right on our unit controller object. So here we have the unit controller script, and I know this video is probably getting really long already, so I'm just going to kind of breeze through the main points here. So basically what's going to happen is when we press the number 1 key, we're going to go ahead and spawn some units into our world, depending on how many units that we've specified up here for the number of units per spawn. And if we hit the number 2 key, we're just going to go ahead and destroy all the units. So you can see here, these are the spawn units and destroy units functions. Basically, it just spawns some units somewhere randomly on the grid, making sure that we're not on an impassable tile or overlapping with another unit. All right, so all the actual movement is happening in the fixed update function. So basically, if there's no flow field, we can just return out of the function. Otherwise, we're going to iterate through every unit that's in our game. Of course, if you've been following along with some of my ECS content, you might see how ECS can kind of work into some things in the future. Anyways, we'll just get a reference to the cell that is below the current unit, and we're just going to be using the get cell from world position, which is the same function that we use to determine which cell that we're clicking on. So once we have that, we can set this new vector3 to the move direction, and we'll set that using the values of the best direction.vector.x and the best direction.vector.y of the cell that we're currently on top of. Now here we'll just get the rigid body component of the unit, and then we'll just influence the velocity equal to the move direction multiplied by the move speed. And the move speed is just one of these public values that we're setting at the top here. So now when we come back to Unity, we're just going to make sure that we remember to set our grid controller, bring in our unit prefab. We'll say do 50 prefabs per spawn. We'll give it a move speed of 3. All right, so when we enter play mode and then we set a destination, of course I've turned off all the arrows so it's a little bit easier for us to see the movement. We can just hit 1 a couple times and you'll see that things start spawning into our world, and then it follows the most efficient path all the way to the destination. We can set another destination and you'll see how it kind of follows the flow field, and it just goes to the destination just how you want it to. I mean, can't be simpler than that, right? So I mean, I definitely do hope that you guys go ahead and implement your own flow fields, because these are a ton of fun to play with. Again, this is just kind of the mono behavior implementation of all of this, and I do want to use ECS and the data-oriented technology stack to see if we can come up with some more efficient versions of the flow field pathfinding. You may have already noticed some places where the entity component system would do really well for these flow fields. So anyways, I'm super excited about that. I hope you guys are all too, so make sure you are subscribed to the channel so you don't miss out on any of those videos. By the way, if you do have any questions on any of this or suggestions for any upcoming videos, you can always leave those down in the comments section below. I really hope that you learned something today. If you did, I'd really appreciate if you hit that like button. Don't forget, you can also download the project files from this video using the link down in the description below. Anyways, that's it for today, so I hope you have a fantastic rest of your day, and I'll see you in the next one. Dang, I've been recording for over 2 hours at this point, and my computer is starting to melt some cables. Oh well.